What's up guys, and welcome to this tutorial on the 2018 supplementary exam. We're going to be going over question 5, momentum, work, energy and power. Okay, so let's get straight into it. Okay, a lead bullet of mass 5 grams is shot vertically upwards into a wooden block of mass 195 grams, which is at rest over a hole in the table. Ignore air resistance. The bullet hits the block with a velocity of 200 meters per second. The bullet embeds itself in the block. Okay, so first up we have a nice definition. 5.1.1. Okay, so state the law of conservation of momentum. Okay, so basically the total linear momentum of an isolated system remains constant. Okay, and what does this tell us in terms of an equation? Obviously you don't have to put this in your definition, but basically it's telling you that the P total before is equal to the P total after. Okay, where P is your momentum, or P is your M times your V. Okay, cool stuff. So 5.1.2, calculate the speed of the block and the bullet immediately after the bullet has embedded in the block. Okay, so basically we need the momentum before. Okay, but before we know that there are two systems, the block and the bullet, and after there's only one system, which is the block and the bullet, which are embedded together. And also remember, our masses are in terms of grams here, where they need to be in terms of kilograms. Okay, so I'm just going to write down the equation. Let's say, okay, so let's say mass of the bullet, velocity of the bullet, plus mass of the block, velocity of the block, is equal to mass of block plus bullet times the velocity final. Okay, so we're working with the bullet first. So the mass of the bullet is 0,005 kilograms times the velocity of 200 meters per second. The velocity of the block is 0, so everything becomes 0, is equal to, so it's going to be 195, so 0,195 grams or kilograms plus 0,005 kilograms times the velocity final. Okay, in this equation, Vf is the only unknown, and so we can solve for Vf, which is equal to 5 meters per second. And it asks for the speed, so there is no units, or not units, but no direction. Okay, and we get ourselves 4 marks. Okay, next we're going to go on to 5.1.3. Okay, so 5.1.3 says calculate how high the block will rise above the block's original position. Okay, so how we're going to do this, we're going to use conservation of energy. Okay, and conservation of energy says that EK plus EP before is equal to EK plus EP after. Okay, so before means before the block has moved up, and after is at the maximum height of the block. Okay, so okay, so we have EK is going to be a half times the mass. The mass is going to be the mass of the block and the bullet, so that's 0.2 from this part right here, times the velocity squared, which was the velocity we calculated before, so 5 squared, plus, remember there's no potential energy here, so plus 0 equals, and then at its maximum height the velocity is 0, so there's no kinetic energy, plus the mass again, 0.2 g 9,8 times the height. And again we have only one unknown here, which is the height, so solving this we get h is equal to 1.28 meters. And that's our final answer. Cool stuff, and we get 4 marks as well. Great stuff. Okay, Question 5.2. Okay. A crate of mass 70 kilograms. A crate of mass 70 kilograms slides down a rough incline, which is at an angle of 20 degrees to the horizontal. The crate experiences a constant frictional force. Okay, so we have to start off by drawing a free body diagram. Okay, so not too difficult. Let's give ourselves a 20-degree slope right here. So this is 5.2.1. Okay, and then we have the crate, and we definitely have weight acting downwards. We know there's a frictional force and the block is moving down, so the frictional force is going to be acting upwards. So let's call that force friction. And obviously there is a normal force. So okay, then it says which force in your free body diagram does no work on the crate. Okay, so that would be the normal force. The normal force does not do any work on the crate. So 5.2.2 would be the normal force. Okay, and we get ourselves 2 marks. Okay, then it says the crate passes point K on the incline at a speed of 4 meters per second before passing point L 18 meters lower down on the incline. Calculate the kinetic energy as it passes through K. Okay, so we want the kinetic energy as it passes through K. So not too difficult. Let's see, let me give myself some space. Okay, so the kinetic energy as it passes through K, let's do it here. 5.2.3. EK is equal to a half mass times the velocity squared. A half times our mass of 70. We know the mass weighs 70 kilograms. And we know that as it passes through point K, it's going at 4 meters per second. So times 4 squared. And that gives us 560. And the units of energy is joules. And that's our final answer. We get ourselves 3 marks. Okay. Calculate the magnitude of the resultant force acting on the crate between points K and L. Okay, so basically we want F net. So 5.2.4. So we want the resultant force. So we can say that F net, okay, so F net equals what forces are acting on the slope, and we're going to take, let's say, the downward force as positive. Okay, so we know that there is a component of the weight that is acting downwards, right? That is acting in that direction that we actually care about. Okay, and we know that angle there would be 20 degrees. Okay, so the sum of the forces, so that would be a positive force downwards, so that would be mg, that's your weight, and then sine 20, okay, minus the force of friction. Okay, so we know the mass is 70, 9.8 times sine of 20, minus, we know the force friction was constant, and it had a value of, let's see, 190 newtons. 90 newtons. So the net force acting is going to be equal to 44.63 newtons. And that's the net force, F net. Okay. Then it says, state the work energy theorem. Okay, another definition. So 5.2.5. Okay, so basically we can say that the work energy theorem says that the work done by a net force is, or work done on an object by a net force is equal to the change in kinetic energy of the object. Okay, and that's the definition. Then the last question, 5.2.6. Okay, so it says use the work energy theorem to calculate the speed of the crate as it passes through L. Okay, so the work energy theorem basically says the formula for it is, let's see if it's on the phone. No, I don't have it open. Okay, so basically F net times your distance, or your change in S, is equal to your change in EK. Okay, do we know our F net? Yes, we do. We just calculated it as 44,63. Do we know the change in S? Let's go look. Our diagram says it is 18 meters times 18 is equal to, change in EK is equal to a half times your mass, which was 70, times your V final squared minus your V initial, which was 4 squared. Okay, and if we look at this equation, the only unknown is Vf, so we can solve for Vf is equal to 6,24 meters per second, and that is our final answer. Okay, yeah, and that's basically that. We get ourselves a full 28 marks. So I'm happy with that. Yeah, so I hope you guys found this video useful. Yeah, thanks for watching, guys.